Bismillahirrahmanirrahim. So today's topic is heat engine. If you remember in the last class, we already discussed about this. Okay, I gave you a little bit of idea that what is heat engine. Heat engine is something that we can take heat from some source, from a heat source. It will take some heat and it will convert into work. Okay, so that is called some heat engine. Okay, so let us see, we will study in details. There is a figure given also 1.8. If you see at the page number 25 on the right, at the middle of the page, a figure is given which shows the heat engine. Looking at the heat engine, we actually get the idea that what it is doing. See, there is a heat source at the top, right? And from it is deriving some amount of heat, and from the amount of heat energy that it is drawing from the source, a little bit of that amount or a part of that amount is converted into work, which is shown by arrow that it is going out, and the rest of the heat that is left given out, okay, that is given to the sink. Acha. So if I go through the lines of the book, it will be like this. To use heat energy, we need a device. Yes, we know this. If I want to use the heat energy, I need a device, and that device is called heat engine. Definition: the device which converts heat energy into mechanical energy. Always remember this one. Heat engine, the purpose of heat engine is to convert the heat energy to some other kind of energy, right? Sometimes I see the students making this mistake. In my times also, I used to see some of my friends making this mistake. They used to write to convert the mechanical energy to heat energy. No, heat energy to mechanical energy. Okay, if I want to convert the mechanical energy to heat energy, I can do it by my rubbing my hands itself. I do not need any heat engine. Mechanical energy can easily be converted to heat engine, but heat energy cannot be easily converted to other form of energy. For this, you need a device which is called heat engine. Okay, so the purpose of heat engine is to convert the heat energy to some other kind of energy. Let us say this is mechanical energy because this is the energy that we need most in our daily life. Okay, so engine absorbs a certain quantity of heat from a source. Yes, definitely there must be a source from where I will gain the heat. I will take the heat and do some work using the heat, right? So engine absorbs a certain amount of heat from a source, converts a part of it into work, and rejects the remaining heat to the surrounding. It is like taking the money, using the money to do something, and the rest of the money you save it, okay, or you give it to someone else, okay, or you can say you donate it, okay. Now the temperature of the source from which the engine absorbs the heat should be higher than the surrounding to which the engine rejects heat. This is very understandable. If the temperature of the source is not higher, then the heat will not flow to the lower temperature. This one we understand, right? The temperature of the source must be higher, then only we can draw some heat from it, right? Okay, so that is, the engine absorbs heat from a source of higher temperature, converts a part of it into work, and rejects the remaining part of heat to a sink. Sink মানে it's like dustbin. Okay, sink to a lower temperature, and the initial condition is restored. Okay, so we will see what are they trying to say. If you take a look at the figure, in the figure we can see that there is a source, heat source, right? And it is at higher temperature. So as a result, what will happen? In between, we have this heat engine. So what will happen? The heat will flow in this direction. Okay, the heat will come here. Now what will happen? This heat energy will use the heat energy drawn from it to do some work. Let us say I have done a certain amount of work, that is W. Okay, and the heat that I drew was Q1. তো Q1 থেকে আমি W amount of work করে ফেলছি। তাইলে এখন কি হবে? বাকি যে হিটটা আছে, ওকে, সেই হিটটাকে আমরা কি করব? সিঙ্কের কাছে দিয়ে দিব। And the sink will be at lower temperature so that it is able to receive the heat. Do you understand my point? If the sink is also at higher temperature, then the sink will not receive it. Rather, it will also supply heat to the heat engine. But the heat engine needs to leave, or liberate the unused heat energy, right? So that is why, to give the heat, the sink must be at a lower temperature so that it is able to receive the heat. Okay, so now what I can see, let me give you an analogy using the money. If I give you 10 BD, okay, I gave you 10 BD, that is the money supplied. So from that, let us say you wasted 2 BD, you wasted 2 BD, that means the energy that you wasted or the money you wasted is Q2. So if I ask you how much money you have used, so what will be your answer? I gave you 10 BD, 2 BD you have wasted, so how much you have used?
8.
8 BD. How did you find that out? The supply minus the wasted, that is the amount used, correct? So can I write W is equal to Q1 minus Q2? I supplied you Q1, out of that Q1 amount, Q2 amount you have wasted. So Q1 থেকে Q2 যেটা তুমি ওয়েস্ট করে ফেলছো সেটা যদি আমি মাইনাস করে দিই, তাইলে I will get the amount that you have actually used. So this is the work done, and this is what I am interested in. I'm not interested in the energy wasted, I am interested in the amount of work done, because the purpose of heat engine is to produce some work, or we can say convert the heat energy into some work. তো কতটুকু ওয়ার্ক আমি পাবো সেটা আমরা ইজিলি বুঝতে পারি। আমাকে যতটুকু সাপ্লাই দেওয়া হয়েছিল ওখান থেকে আমি কিছু নষ্ট করে ফেলছি, তো যতটুকু নষ্ট করে ফেলছি ওটা বাদ দিয়ে দিলে যে অ্যামাউন্টটা ছিল সেটাই আমি কাজে ইউজ করছি। So do you have any doubt regarding this figure? The temperature, higher temperature, let us consider to be T1, and the temperature of the sink which is at low temperature, okay, let us say this is T2. So from here actually we can say T1 must be greater than T2. Okay, so now let us go through the lines of the book. I will read the bold line that is written at the middle of the page. That is, the engine absorbs heat from a source of higher temperature, converts a part of it into work, and rejects the remaining part of heat to a sink of lower temperature, and the initial condition is restored. Okay, then to get continuous supply of work from an engine, the cycle of the operation are to be repeated. Okay, so one cycle has been completed, again another cycle will be repeated, and another cycle will take place, then again another cycle, so the same cycle will be repeated to get a continuous work. Okay, do you understand my point? আমাদের বারবার এটা রিপিট করতে থাকতে হবে so that we get continuous supply of work from it. Okay, আচ্ছা, now since the cycle of operation can be repeated indefinitely, therefore the heat engine gives a continuous supply of work indefinitely. Let a working substance such as gas in a cylinder fitted with a piston, that is the arrangement actually we have been thinking since the commencement of this chapter, right? Okay, so a gas is inside a cylinder, one side is fixed with a piston and other three sides are fixed. Okay, now absorbs Q1 amount of heat from a heat source of higher temperature T1. They are just describing what I have already talked about, right? So Q1 amount of heat it will draw, out of that it will produce W amount of work, and the rest amount of heat it will leave to the sink. Okay, so this is what they have talked about in the rest of the paragraph. So I would I would prefer not wasting time reading those lines. I would like to request you to go through these lines, and if you have any doubt you can ask me in the next class, inshallah. So kindly go through rest of the paragraph. I would like to start from Carnot's engines now. Carnot engine, the pronunciation you might feel like to be Carnot's engine. Actually in practical it is pronounced as Carnot engine. Carnot, T is silent. Okay, Carnot engine. Okay, acha. So let us see what is Carnot engine. Heat is converted into work with the help of a heat engine. That is what we have talked about till now, right? The engine which we use in practice cannot convert all the heat into work. That is why some amount of heat it is leaving to the sink, right? A significant amount of heat it is. Let us continue. Okay, so Carnot engine, heat is converted into work with the help of a heat engine. The engine which you use in practice cannot convert all the heat into work. We know this, right? Certain amount of heat we will draw, but not all of it we will convert it into work. Some amount of heat we will have to leave to the sink. Okay, acha. Generally the engine can convert maximum of 25% of the heat supply. Okay, see, this is very less actually. If you think, if you supply 100 joule of work, it will convert only maximum of 25 joule into work. If you supply 100 joule of heat to a system, it will be able to convert 25 joule out of it into work, and the rest 75 joule it will be wasted. So see, the efficiency is actually very less. Okay, so generally the engine can convert maximum 25% of the heat supplied. A French engineer, Nicolas Leonard Sadi Carnot, okay, so he lived from 1796 to 1832, conceived an ideal engine, okay, which is free from all the imperfections. This is an imagination. Okay, as you know, in case of ideal gas, we know that there is no ideal gas in practice. That is why we have to imagine it. Likewise, Sadi Carnot, he imagined an heat engine which is above every imperfection. It is perfect. Okay, it will not actually lose any heat. Okay, whatever heat we supply to it, it will totally convert into work. Okay, so as this is not possible in practice, we understand that this is an imagination. Okay, so that is why it is said that he's conceived an ideal engine. This is ideal, not real. Okay, so which is free from all imperfections of an actual engine, which is known as Carnot engine. It was named after his name. Okay, so let us go through the definition. Sadi Carnot conceived an ideal engine to convert heat energy to mechanical energy. This must be there, because this is the sole purpose of using a heat engine, right? Heat energy converted to mechanical energy, which is free from all imperfections of an actual engine. Actual engine is the one where we will not be able to convert all the heat to work. That is the actual real engine. Okay, so actual engine will have so many imperfections. The engine that Carnot conceived is above all imperfections. Okay, so this is Carnot engine. The Carnot engine is only an imaginary one written in your book. It is not possible to construct such an engine, okay, in practice. The different parts of Carnot engine are shown in figure 1.9. Okay, so we will see how Carnot imagined or conceived the engine. There are several parts of it. Okay, we will get to know about each of the part. Then there is a Carnot cycle. We will do some kind of operation one after another, and this operation all together they are known to be as Carnot cycle. Okay, this cycle will be repeated and repeated. Okay, Achha, so let us go through the different parts of it, because if you want to understand the Carnot cycle, it is very important to understand the work of every part. There are 4 parts of it. Okay, if you take a look at it, number 1 part, a cylinder C. It would have been better if I could have shown you. Okay, let me draw it on the board. Even though if you have the book in front of you, then actually there is no need to draw, but still I'm drawing so that I can discuss it in a more efficient way. Now this shaded part actually represents insulated. That means if you have an object, you make it come into contact of this box from this side, what will happen? No heat transfer will occur, because there is an insulator on this surface. But what will happen if you bring it and keep it here? If you place the ball here, then okay, heat energy transfer can take place, because this top part is not insulated. So as it is given, this is the heat source. Heat source. So definitely it must be at a higher temperature, which we consider to be T1. Okay. Then there is a heat insulating material. Heat insulating material means this prevents the transfer of heat. Okay. Then we have a sink. Sink means where we will reject the unused heat. And again, this is kind of similar to the heat source. Okay, in 3 sides it is insulated, so as a result there will be no heat loss along these three surface, but heat transfer can occur from the top. Okay, so this is the sink which will be at lower temperature, which is T2. Okay, now we have a working cylinder. This is the working cylinder where we will actually keep the gas. So this is the piston. Okay, so this is the cylinder in which we are keeping the gas working, and the working substance, that is gas, working substance, that is the gas, it will be inside this. Okay, and this P represents the piston actually. Okay, so now let us go through. Number one, a cylinder C with perfectly non-conducting wall. See here, I actually forgot to show it, that this walls will be non-conducting. Non-conducting means they will not conduct any heat. That means they are made of insulating material. Okay, so as a result, through the wall there will be no heat transfer, only through the bottom part heat can be exchanged. Now why it happened that I kept the top surface of the heat source as the heat exchanging way, and here I took the bottom part at the heat exchanging way? It is because so that I can, when I keep the cylinder on this one, you see through the bottom and through the top surface of this, they can exchange some heat. Okay, due to that we have kept it the arrangement in this way. So it is fitted with a perfectly non-conducting and frictionless piston. The piston here is also non-conducting. That means the heat cannot escape through the piston. Okay, this is also non-conducting. An ideal gas is enclosed in the cylinder, which acts as the working substance. Yes, there is a gas inside it, right? Achha. The heat source is a hot object. It is, heat source must be a hot object, right? So that we can draw some heat from it. With a very high thermal capacity is maintained at temperature T1, any amount of heat can be taken out from it without changing its temperature. Okay, so what we are doing it, we are taking out the heat from it. As a result, the temperature should have gone down. No, we are doing something so that the temperature remains the same. Okay, if the temperature comes down and the heat and the source becomes cool, then what will happen? We cannot repeat the cycle anymore, right? If I want to get a continuous flow of work, I must keep the cycle repeated. And if I want to keep the cycle repeated, you understand that this source must be remaining hot or at all the time. So the temperature T1 cannot be decreased. So some kind of arrangement has to be made, so through which we can actually keep the temperature of the heat source fixed. We can draw any amount of heat from it. It is like the bank. Okay, it is the bank from which I can draw as much as money as I want, but it will never become poor. Okay, it will always be rich. Okay, now the heat source is an hot object with very so we understood this. Number three, the sink is a cold object. The sink is a cold object with very high thermal capacity is maintained at a lower temperature of T2. Any amount of heat can be rejected to it. I can give any amount of heat to it, but what will happen? Without changing its temperature, that means T2 will not change. What was supposed to happen? If I supply some amount of heat to the sink, as a result the temperature T2 should have gone up, right? And the sink should have become hotter, but this cannot happen. I cannot let this happen. Why? Because if the sink is not cool anymore, if the sink becomes hot, the temperature of the sink increases, it will not receive any heat that I give it, right? So it is like a poor person who should always remain poor. Okay, so that I can give him some money and he can take it. Okay, so I will always give him some heat, but he cannot become rich. He has to remain always, actually not rich, he cannot become hot. Okay, he has to remain cool always. Acha. So this is the sink, a platform made up of completely insulating object, that we are talking about this element now. Okay, so this is the platform which is made up of heat insulating material on which the cylinder is placed. Initially the cylinder I will place on this one. Okay, later we will actually put it on this, then sometimes we will put the cylinder on the sink. So this is the stages, okay, that we are going to see in the Carnot cycle. But before I start the Carnot cycle, I want to ask you, do you have any doubt in the components of the Carnot engine?
No, sir.
No. Excellent. Okay, fine. So actually what I'm afraid of is, how many minutes are left? 7 minutes. Okay, no problem. 7 minutes is not less. What period do you have next?
Biology.
Biology. Okay, and you are so much interested to do that class, I know. That's okay. So I will try to finish this Carnot cycle within 7 minutes, but I don't know whether I can or not. But let us start at least. Okay, let's take a try. So Carnot cycle, if you see, the definition is given. The working substance is taken through a cycle of operation, which I already told you, right? This working substance, sometime I will heat it, sometime it will leave the heat, sometime it will be placed on the heat insulating material, so no heat can escape. So a couple of operation, one after another, we will take it through. All of the operation together are called a cycle, which is called Carnot cycle. Okay, a cycle in which the working substance starting from a given condition of a temperature, pressure, and volume is made to undergo two successive expansion. That means 2 times the gas will expand and 2 times it will compress. Okay, see, it is written that it will undergo two successive expansion, one isothermal and another adiabatic. Out of these two expansion, one will be isothermal. That means in that expansion I cannot let the temperature change, and another one is adiabatic. That one will take place when we will not allow any heat to escape or come in. Okay, because in adiabatic process the amount of heat remains constant. Okay, I can see Sajid has joined for the second time throughout the online class history. Acha. I wish I could have, given you a red carpet welcome, but I'm not being able to do. Please do not mind and attend the class.
স্যার অনেকক্ষণ আগেই জয়েন করছি স্যার।
Acha, acha. Good, good. Okay. Now, a cycle in which the working substance is starting from a given, it is foreseen already, and then two successive compression, one isothermal and another adiabatic, and then brought back finally to its initial condition is called Carnot cycle. So what is going to happen? One adiabatic expansion, one isothermal expansion, another adiabatic compression, another isothermal compression. So as a result, I will travel a whole path and will come back to the initial point, and then the cycle will be completed. That cycle is called Carnot cycle. Now we will go through each of the 4 steps. If you have noticed, there are 4 steps: 2 adiabatic expansion and compression, 2 isothermal expansion and compression. Okay. মোছার কথা ছিল না, আচ্ছা যাই হোক, বেশি মুছি না। So this is heat insulator and this is the source. Temperature T1. Okay, fine. So if you take a look at the step 1, okay, the step 1. In step 1, what we will do, the cylinder C is placed on the source. That means this cylinder will be kept on the source. Okay, if I keep it on the source, you can see that it can receive heat from the bottom and it can give heat from the top surface. So as a result, what will happen? This working substance will receive heat and it will expand, right? Okay, so the cylinder C is placed on the source, and within a very short period the gas attains the temperature of the source, right? So heat exchange will take place until the temperature of them become equal. So it will become the temperature which is equal to T1. Okay, now let at this stage the pressure and volume are respectively P1 and V1, which is represented by the point A of the indicator diagram. So we have started our indicator diagram, which is also shown in your book, figure number 1.10. So from where we are starting our operation is represented by the point A, and the pressure and volume is P1 and V1. So as you know that we represent pressure through y-axis and volume along x-axis. So if I draw along this line a perpendicular, this will be V1 and this will be P1, right? Okay. Then which is represented by the point indicator diagram. Now the ideal gas is allowed to expand isothermally. Now we do not want to the gas to increase the temperature anymore. So what I will do, I will let it expand. So if I let it expand isothermally, the temperature will not increase. As a result, I have to let it expand. If I do not let it expand, the temperature will definitely rise, because that time the pressure, the volume is being kept constant. But if I let the volume change, the temperature can be kept constant. So, and at the end of this process, its pressure and volume becomes P2 and V2. So, what I did, I wanted to keep the temperature constant. As a result, I had to let the volume increase. Let us say the volume has become this. Here, as the volume increased, the pressure will come down. Do you disagree with this? We already studied this in Boyle's law, right? So if the volume increases, the operation will go something like this. As the volume is being increased, the pressure is coming down. So at this point, the volume has become V2. It has increased, but the pressure, it has become P2, which is less than the previous pressure. So at this point, B, the pressure P2 and volume is V2. Okay, so this is our isothermal process. If you remember, we already studied about the curve of the isothermal process. It is supposed to be something like this, right? Acha. Okay, so then what we can see, so that point is represented by B on the indicator diagram. Okay, so what is the amount of work done in this first process? W1 is equal to P dV. Now, as we are differentiating with respect to V, so the limit, the upper limit and lower limit should be in terms of volume. So volume, the lower limit, the initial volume will be the lower limit, that is V1, and the upper limit, that is V2, should be the what? That is the final volume, right? Okay. So if I ask you that from the indicator diagram, can you show me the work done? You can show me. How? Because it will be the area under the curve. As we already know, from the PV diagram, if I want to calculate the area, all I have to do, I have to calculate the area under the curve. Okay. So they have drawn the perpendicular and given this point. A point will naam dise E or eta G. So A, B, G, E. This is the area under the curve. If you calculate the area of this A, B, G, E, then we can easily find out the work done for this process. Okay. Now all the rest three process are similar, and I can see that discussing about the step one only has brought us to the end of the time. We are already 1 minute over the time. So what I will request you, all the three steps are quite similar. Okay, so kindly go through. We will discuss about it in the next class, inshallah. Okay. So thank you for joining. Assalamu alaikum wa rahmatullah wa barakatuh. See you in the next class.